So, even before we get into the math part of radial basis function, I just wanted to draw an analogy with some stuff that you might already be aware of. How many of you know finite element here or has some exposure, have taken a course on finite element? Surprising, because I thought that all of you have a structural background. Anyway, the idea behind finite element is very simple. Okay. I mean, I will try to explain it with the context that what we want. Okay. Let us not get into finite element as such. Finite element is also a numerical approximation where you do not have a closed form solution. Okay. So, a simple cantilever beam, of course, finite element can solve more complex problems. Okay. The idea is, this is your deflection function, but this function also could be complex, that is one thing. The second is, I do not have an explicit, pretend, imagine that I do not have an explicit equation to compute the deflection. In this case, I know it is PL cube over 3A. The moment this structure becomes complex, I do not know what the deflection is. There could be multiple loadings. So, in such situations, what is advised is you divide this structure into finite number of elements, that is what is finite element methods or analysis, right. After this, what you do, using the known mechanics, not for the entire structure, but for each of these guys, you can solve for the displacement and the what do you call the stresses or whatever the quantity that you are interested in. Usually, we solve for the nodal displacements, because at the nodes is what you have the information. The moment I say nodes, it means there are different types of elements that you can use. The finite element that I am talking about, you can use different types of elements. Since this was just a beam, you need to use something called a beam element in this particular case. Let us say that you are interested in something else that is going to vary across the cross section. Okay. And if you had a surface, let us say, then the surface can be approximated by triangles, for instance. Yeah. So, I can keep approximating this structure into triangles, and there are also, I can also use a rectangular approximation if there is a need. The point is, each of this is an element. Okay. The point that I want you to appreciate is, each element has a node. What I will do is I will look for the solutions at each of these nodes. I will find out the displacement at each of these nodes, but that is not that might limit my solution, right. I know the solutions only at the few locations. We know a simple way by which I can interpolate these 4 to find out the displacement or stresses or strains wherever I want across the structure. This is the overall idea of finite element. Okay. So, it is a simple stuff that you want to know is F equals Kx is what you are going to use. K comes from the stiffness matrix. It is a stiffness matrix, basically based on the geometry and the material property you can get it based on how you are discretizing, that is all. X is something that you are going to solve for, F is something that you usually know. You know what the displacement is, what the force is, and you know where you are applying it. Accordingly, there are certain elements will go off in this K, and basically you need to do a matrix inversion to find this X, but it is not that straightforward, because I could have million nodes here. Doing a million by million inversion could be a problem, and there are some mathematical tools that lets you do this. Okay. This is the most simplistic way of looking at it. Okay. There is a nice geometric way of looking at the same problem. What you are actually trying to do is, okay, what is the difference between a triangular element and a rectangular element? Okay. The triangular element requires only 3 nodes to describe it, whereas a rectangular element requires only 4 nodes. What does that mean? Though I give 4 nodal information for this guy, meaning I will have to calculate 4 nodal information, which means I need a higher order equation. There are 4 unknowns, whereas in this case there are only 3 unknowns. Whereas just now we saw with 3 unknowns or with 2 unknowns, with 2 unknowns for a linear line, for a linear, you can only approximate a linear fitting. Okay. If it is a quadratic fitting, then there are 3 unknowns. So, similarly, when you are trying to solve for more unknowns, it means that your approximation is higher order. It is not necessarily true that your approximation is better, it is of higher order, that is all. Okay. Just because you are getting a master's does not mean that you are knowledgeable than a undergraduate student. Okay. But getting a master's degree enables you for a higher order degree, that is all. Okay. That is what is the idea, but you will have to subject yourself for another couple of years of education. So, more the information, okay, or more the unknowns that you need to compute, the larger should be the number of points. So, that is the idea. So, there is more computation for a rectangular element compared to a triangular element, but this is likely to let you model a higher order compared to the triangular element. Okay. So, now what happens is the whole idea is I am going to approximate this curved line which represents my deflection using multiple approximations. Okay. I am not going to just construct one line, I am going to approximate it for each of these elements, right. So, if I use a linear approximation or let us say a constant approximation, that is what a bar element does. Okay. The bar element does not vary along the length, okay. It does not take bending, right. So, let us say that I use a bar approximation. What it means is I will have my displacements like this. Okay. So, which is not correct. So, my displacement should be continuous, it cannot be like this, okay. But that is okay, this is okay, this is the overall idea. Okay. If you have a circle, let us say you do not know how to find the area of the circle or the perimeter of the circle, but you know how to find the perimeter of a triangle. So, what you can do is you can use multiple triangles and you can find what the perimeter is. It is likely to be lesser than the actual perimeter. Okay. There are two things, this is a lower limit because your this is inscribed, okay. Whereas, if the circle is inscribed, you can do it like this also, you can go out and inscribe the circle inside the triangle. So, that will be your upper limit. What might be a what should I do here to get a better approximation of my circle's perimeter? I should increase the number of triangles. You get the idea? Okay. This approximation will be better than what I got earlier. Now, if I further divide my triangle, I will get a even better approximation. Okay. So, but then I will have to solve for 2n, then 4n type of elements, not type, number of elements. Okay. So, the number of computations increases, but I will get a better approximation. How good of an approximation you want is what the designer takes a call at. Okay. And at some point in time it will converge. Should I use 100, should I use 1000, or should I use million elements or million triangles in this particular case? You can look for the perimeter convergence or area convergence, whatever the quantity that you are trying to do, you can look for a convergence. Okay. After beyond a certain, it will given to the total number of computations that you are doing, the gain in the error or the percentage by which you are reducing your error will go down miserably. Then you stop at that point, that is what is called. So, in a similar sense, okay, I am trying to do this. What could be a better approximation is, yes, I could use more number of elements, that could be one stuff. Okay. Still what you are trying to do is you are trying to do this. I do not know whether you are understanding. If I am going to zoom this, what it means is, okay, it's actually not even that, it should be like this. It's a step function. Okay. What I could do still, because what do I need to know to represent this particular line? No, points is okay, but unknown wise, not even 2 points in this case. You need only, this is a constant line, So, primarily okay, you just need to know x equal to c or y equal to c, that is all, but the c varies, it is C1, C2, C3, C4 like that, okay, but it is only one that you need to find. Naturally, what is my higher order information? I need to be able to find two unknowns. So, two unknowns means what? I can do this, correct. So, now I am going to redraw that guy here, so that okay. So, what it means is I can do this. Okay. Actually speaking, I should draw on top of it so that you understand. Still I might have this issue. Okay. Why? Because this guy is P L cube over 3 I. He is a cubic. What am I doing? I am trying to represent that guy using a linear line. Okay. It is varying, this is the L. So, L1, L2, L3, L4. L4 is still varying in a linear sense for me. So, I might still get this error. If I keep zooming, that error will be large actually. Okay. So, how can I reduce? There are two ways in which I can reduce. One is increase the number of elements. Okay. So, it is still linear, but then you will, that is one way of doing it. The other way obviously is to go for a higher order element. Okay. So, instead of using a linear approximation, I will use a quadratic approximation, but then quadratic approximation requires 3 unknowns in 1D. It requires 3 unknowns. So, which means that you need 3 nodal points within an element, that is the concept of finite element. Okay. The whole idea here, what I want you to appreciate is, of course, it is great if you appreciate the nodal points and finite element and all that, but what I want you to appreciate is we are eventually interested in the shape of my deflection, shape of my stresses. Yes, there is a math that is inbuilt into it, but what is it that you are trying to look at from a end user perspective is there is some shape that this guy is going to deflect. I want to approximate that shape, so that I can visualize, I can make decisions. So, I do not need to approximate the entire deflection, but I will go and approximate it in a linear sense. So, if the approximation itself is bad, then I will use more number of elements, that is one way of doing it, or I will enable a better approximation, so that I can use a lesser. There is always an argument, okay, because you still the number of coefficient versus the number of computations that you need to do, okay, which is better. There is always a debate on all those stuff, but the idea that I wanted you to appreciate here is you are trying to approximate a shape. That is exactly what we are trying to do in the meta models also. Okay. So, you are there is a shape and you are trying to model the shape. This shape could be like this, or this shape could be like this. You want to model these x1 y, x1 and y, x1 and y. The only point is you do not have these here, also you do not have, you are only creating by interpolation, you do not have this curve. Instead, what you have, sorry, and then it is likely that this is going to be the fit for this guy. Okay. I just give you a set of points, can you give me the curve? That is what we are going to look at. And in a similar way, this can meaning, but in this case we are looking at a continuous function, we are not looking at a, but this continuous function, see eventually here also what in finite element also what you do is this, though you are estimating it in every element, there is also some continuity equations that we enforce. Okay. This for instance, this step function is not allowed. Okay. There is some continuity equations, C1 continuity, C2 continuity is something that you need to bring in, because you will not stop with displacement, you want to identify strains. Okay. So, the displacement is just the entry point, you want to identify strains for which it should at least be C1 continuous. Okay. So, there are some continuity conditions are enforced. In a similar sense, here you want to find a smooth function. Okay. But the only point is, maybe each of these functions can have different basis functions, you are only going to linearly sum them. Here also the idea is only linear summation. What we do is usually we write it like this, NIUI. U is the displacement, NIUI means it is the shape function. Shape function is the interpolation function for each of these guys, that is all. Okay. How you are going to interpolate? It is in a linear sense or in a non-linear sense or in a quadratic, whatever, not non-linear, quadratic sense. UI is the displacement at each of the nodes, that is all. So, once you find the nodal displacements, it is only a linear superposition, and this holds good, this is it. Any complex, so you go for any kind, today people are using radial, any NURBS, non-uniform radial basis systems, okay, to model these displacements. There also it is still NIUI, because I am eventually going to find my nodal displacements and I will do a linear superposition of it to find what my total displacement. In a similar sense here, I want to approximate this function at, not at, around each of those points, but I will add them, that is the overall, and that addition will be a linear superposition is what the overall idea is, but you can also do a different types of superposition. Okay. So, this is something that I want you to appreciate, and we will go into radial basis function. What I will do is I am going to skip a couple of slides to begin with, and then yeah. So, we will start with this, because right now I gave you the analogy of finite element, we will start with this and then I will go to the math part. So, you will, I hope you will be able to appreciate this better. Okay. So, I have 3 data conditions here. Okay. So, this is the value of the point at x1, this is the value of the point at x2, this is the value of the point at x3. I have only 3 data points. Now, what I am saying is, this is what I told you, right. I want to have some function, okay, here, and let us call this the radial basis function I. The form of the function is the same, because as you remember, when I did the approximation for the finite element beam, the form of the functions were the same. There were multiple such functions, right. It was just a linear line, I mean it was either a constant line or it was a linear line. The values they took were different, but they were, the forms were the same, they did not change. In a similar sense, the form of this, we will see what this form is. Okay. The form of this radial basis function is the same, but I am going to use many of these radial basis functions. How? Okay. For instance, this psi describes the function, the form of my function. Okay. Yes, it is measured in terms of the x wherever you want to estimate minus the x1, along which you center your radial basis function. Okay. See, if you just thought about it for a couple of seconds, it is very simple. It says radial basis. It is a basis function, it is in a radial sense. Radial means what? Okay. This is a point and it is in a radial sense. In a radial sense, it increases or decreases. Okay. So, this is in a top view perspective. If you look in the front view kind of stuff, this could be one stuff. Okay. It is around a center and it either decreases or increases towards the center. I mean, it decreases away from the center or increases towards the center. And I could also have a slightly complex description, but this requires a little bit more parameters. It says, okay, here is your center and here is your standard deviation. This is very similar to your Gaussian function, and that is why they are also, the Gaussian functions are also used in radial basis. Okay. And you can say, no, no, I do not want this, I want some kind of an approximation like this. Yes, you can do that. You can also do this kind of an approximation. Okay. So, it is the radial basis, that is what I want you to appreciate. Okay. So, the function is in a radial sense, meaning it increases or decreases monotonically towards your center. That is something that I want you to appreciate. Okay. And of course, you can have it like this also if you want. Okay. The same stuff, it is just a mirror. You can imagine that there is a mirror of the thing, I do not know. Okay. So, now I am just taking this guy. Okay. If you look at it, the only thing that is going to vary in this case will be a function of the height, number 1, and where your x is. Otherwise, it is varying in the same fashion, all these 3 guys. Okay. There are 3 points, There are 3 data points that I know, and I am going to use 3 radial basis functions. The form of the functions are the same. In this case, if you would just call it, it is a linear variation in a triangular sense, okay, linear variation in a triangular sense, that is all. So, the psi, the form of the psi is the same, and it is dependent on where you are going to estimate with respect to x 3, where you are going to estimate with respect to x 2, where you are going to estimate with respect to x 1, that is all. So, the function is centered, this is one way, but you do not need to center it at that point. One easy way of solving this is you center the function at the data points that you have, but there is no need, you can center this here also. Okay. Then what you need to do is you need to find the distance with respect to that center, that is all. Okay. Here if you center it, then the mean or the central point is x 1 minus x 1. So, it will be 0 in this case, x 2 minus x 2, in this case it is x 3 minus x 3. Okay. So, but for at any other location, what you need to do is you need to plug in the x. I know what my x 1 is, I know the form of this equation. So, I will be able to tell you what psi is. So, the only thing that I need to find is my coefficients, these are equivalent to our w's. Okay. Now, what do you think the original function is? It will be a, because the overall point is I am trying to approximate a generic function. So, that if you ask me, sir, can you tell me what x 4 value is, I should be able to tell what my x 4 value is, right. So, now I want to offer a generic solution to you, so that you can put the x anywhere between x 1 and x 3 and you should be able to get your y output. So, what is likely my next step to get the generic function? Sorry, that is all. It is just a linear superposition, just go add this guy and this guy, and how is it likely to look like? It is going to likely to look like this. So, if you understand what is going to happen is, if there are values in this, see plus plus, okay, from here to here only this function exists. So, only that function existed. From here whatever this value is, I will have to add these values also to it. Then for this particular value I need to add this value also. You understand what I am saying, right? Whatever this value was, to that I need to add that value also. Then whatever this value, I will add this value, whatever this value, I will add this value. Then when it comes here, this value will go to 0, but however this guy will start. So, if you look at it, whatever value was here is what will be here, which is nothing but your x 2's corresponding y 2, this will be your y 1, this will be your y 3. You understand, right? So, I am just adding up. See, to even exemplify our understanding, you can imagine that this function goes like this. So, you are fitting functions across your domain, centered at each point. Between the point that you are fitting and the adjacent point, it will vary, beyond that it will be equal to 0. You know what a direct delta function is? You guys have heard what a direct delta function is? The idea is simple, okay. What direct delta function says is, I will take a particular value at x, I exist across the design space that you are talking about, but I will take a value at x 1, at any other point I will be equal to 0. So, the way you write a direct delta function is, x takes a value of x 1, x equal to 0 elsewhere, or y equals, sorry, yeah, y equals y 1 at x 1, y equal to 0 elsewhere. Okay. So, for instance, if it is very simple, if I want to do this, it is a overkill. What you can do is you can have multiple direct delta functions and keep adding all these guys, you will still get this approximation. You understand, right? So, this is what we are going to do. This is how the function approximation is achieved. So, this is a function that I wanted to approximate. I do not know, see the point, here is the point, okay. I do not know whether this is the actual function, this is my output function, my actual function could be this. My actual function could have been this, but the 3 points that I estimated, it was like this, and I assume a linear, in this case linearly varying radial basis function is what I have assumed. So, this is something that you have to appreciate, because you have decided the form, meaning I gave you the form. As a designer, we have decided what the form of the equation is. If at all you believe that it could be this kind of a function, then you should use maybe more number of nodes, that is one thing, or you should use a slightly complex radial basis function, that we will see next. Okay. But we will take a simple case here, we have taken a simple case and we do this. Okay. Kiran, do you have a question you are about to?
Does it pass through the approximation? Does it pass through all the
In the case in which we have built it, it is like that. There is a concept of noise. Okay. So, let us say that these data are experimental and you believe that there is noise into it, then you might want to average it. For instance, this is what I meant. When you see from the top, this is the dot at which you want to center the approximate function that you want, I mean the radial basis functions, and this could be a radial basis function. Okay. So, this is the thing x I and whatever you want x, this could be an x. So, you are going to estimate the function with respect to its center, you understand, right. You say, okay, I want to estimate the function at this point x, okay, x with respect to the center. There could be another point x2, but to the right of it you say from x2. Okay. In this case it is x1, let us say, that is why xi is. Okay. The top view of this is this, the front view of this function is this. Okay. This kind of 2D. Imagine that there is a function here. So, the top view of this is like this. Imagine your thumb, and then like a Gaussian distribution. Okay. There are two distributions that intersects and then that forms your thumb. Okay. If you look at this, it is a marginal distribution. If you look at this, it is a marginal distribution. That is what it is. If you see from the top, it is, that is what. Okay. It is radially varying, and of course, you can have a smaller spread, you can have a larger spread, but the form is governed. Okay. And usually in radial basis, what you do is for instance, in this one, the mean and the standard deviation, right. So, I need to tell, the mean is something that I need to tell where you are going to position this guy. He can go anywhere in this. So, he can go here, he can go here. So, this is one thing, and the other one is the standard deviation. So, in radial basis function, what you usually do is you kind of fix the standard deviation, but in Kriging you can change your standard deviation. Okay. But it allows for a lot of other advantages. You have to be, you will have to do a little bit more math, but the idea is you have control on your standard deviation. Okay. You understand, right. For instance, in this the standard deviation is the same. It is really not a Gaussian function, but imagine that the way the slope by which it is reducing is the same. But what Kriging might say is I could use different standard deviation. This one could be thin, this could, in the same problem, the next function could be fat, the other one could be very thin.